Okay, so I forgot chapter 7 earlier. But this one will be shorter as far as our reviews go, and I'm just going to go over some questions. Let's see, page 111, number 1. Just page 111. Sound wave is created by a transducer that reflects off an object and returns to a transducer. The depth of the reflector is 10 centimeters of soft tissue. What is the go return time? Okay, well, there's 2 ways we could look at this one. Either using the full range equation, but since this is pretty straightforward, 10 centimeters, you could just use the 13 microsecond rule. But let's go ahead and write out the equation. So that's depth in centimeters is equal to the speed of sound in millimeters per microsecond. I just did that wrong. 4 millimeters per microsecond times. Now we're going to go ahead and just put 13 in here for the to prove the 13-second rule. Microsecond divided by 2. Divided by 2 because our range equation is a go return range equation. We don't want to know the distance of both of these together. We only want to know one distance. So that is why we divide by 2. All right. On this equation, we do 1.54 times 13. We're going to get 20. Actually, let's go ahead. It's like 20.02 or something like that. Divide that by 2. We're going to get 10. And that is in millimeters so far. Microseconds crossed off. We're in millimeters, but we normally speak in terms of centimeters. So that last step is just a conversion. So 13 is simply the number that gives us 1 centimeter. So for every 1 centimeter of depth, the go return time is 13 microseconds. Okay, and so the question is, the depth of the reflector is 10 centimeters. Well, so let's just make this a 13 microsecond rule, and 10 centimeters times 13 microseconds, let's see, is going to be equal to 130. 10 times 13 is 130, and we're looking for the time, so the microseconds is all we care about. So this is our basic rule of thumb. Okay. Sorry, my computer's overheating here. Let's see, number 2, sound. I'm just going to read this one, I think. Sound wave is created by the transducer, reflects off an object. The go return time is 26. What is this depth of the reflector? So we do simply 2 times 13 is equal to 26. Or we know that 13 goes into 26 2 times, so the answer is 2 for number 2. Number 3 is sound. What is the distance that the pulse traveled? Oh, number 3 is, this is one that will trip you up. And so let's look at number 3. Designed to be just a little bit sneaky, but you just have to read carefully. Sound wave is created by a transducer, reflects off an object, and returns to the transducer. The go return time is 26. Okay, so we know from just the previous one that it's 2 centimeters deep. What is the total distance that the pulse traveled? We know from the previous question that 26 microseconds represents 2 centimeters of depth. But that's not what they're asking. What is the total distance that the pulse traveled? Down to 2 centimeters and back. It did the trip forward and backwards. Therefore, the answer is 4 centimeters. Total travel. If it's 2 miles for me to go to Albertsons and I drive there, my total trip there and back, of course, will be 4 miles. Okay. Number 4, maximum. Number 4, let's go ahead and the maximum imaging depth during an ultrasound exam is 10 centimeters. Then the sonographer adjusts the imaging depth to 20 centimeters. What happens to the pulse repetition period? We've doubled our depth. Therefore, we've doubled our listening time. And therefore, we've doubled our pulse repetition period. Okay? We go from this depth to this depth. Let's put a little. We go from pulse repetition PRP, like that looks like that, to one that looks like that. We've doubled our depth, we've doubled our listening time. So the same thing for number 5, what happens to the frequency? If the pulse repetition frequency, if this is doubled, if this went up by 2 and pulse repetition frequency is equal to 1 over pulse repetition period, and we know that the pulse repetition period went up by 2, that means the PRF goes down by 2. Okay, reciprocals. Number 6. I want to do 6. I want to do imaging depth and is 10 centimeters adjustment. 6 is the same thing, just the opposite. Number 7. 7's a great example. I did this earlier. This is what I actually planned on doing. And I could pretend to make the mistake again, but that would sound disingenuous. I'll just tell you what my mistake was. I read through it. Sound wave is created by a transducer, reflects off an object, and returns to the transducer. The imaging depth is 10 centimeters in soft tissue. What is the maximum pulse repetition frequency? Well, let's go ahead and do pulse repetition frequency. So one way of finding pulse repetition frequency is if we know the pulse repetition period. That's not what they're giving us right now. So let's do this the way we're supposed to now. 77,000 centimeters in a second is our top number. That's just a number we're going to put in. On number 8, I'll tell you where the 77,000 comes from. I kind of went over it in class, but you know what? In retrospect, I feel like I didn't really. Pulse repetition frequency, that's divided by the depth, right? God. Yeah. Okay, where am I? I'm on 7, 10 centimeters. Okay, 10 centimeters. And right away we can see that we're crossing off centimeters and we're getting seconds, okay? So that actually comes out to 7.7 kilohertz. And so we look and say, oh, okay, letter B. Here's the problem. I did all this for no reason. Read the question, or look, don't read the question actually, because the question's fine. Read the answers in number 7. There's only one possible correct answer because there's only one answer with the correct units. Not so much the kilohertz, but the hertz itself. That's what all this question was asking, was the hertz. And this is what I did before. I worked it out and found 7.7. I was really proud of myself. And then I looked at the what the answer, B, correct answer because the units are correct. And then I realized I wasn't paying attention to the whole question and answers. So I could have avoided the math and gone quickly, just hit B and moved on had I paid attention. So I am just as guilty as you guys are for doing that kind of stuff. So tis what it is. All right, number 8, sound is created by a transducer. I think this is going to be pulse repetition frequency again, right? And for that, we're going to do 77,000 centimeters per second. And what are they giving us? Yeah, they're giving us the depth, 7.7 centimeters. Now, there's a couple of things. Let me just pause here before we go and answer the rest of the question. 77,000, I think I read through, here, let's read through it again. Speed of sound in soft tissue is 154,000 centimeters in a second. So it can travel into tissue and return from a depth of 77,000 centimeters. So 154,000 centimeters per second, but that's one way, or total distance anyway. So divide that by 2 and we get 77,000 centimeters per second. So this is 77 represents our go and return. All right, so that is why it's 77. And then we put our depth down here and divide into this. Now, here's the other thing I want to mention. So our centimeters cross out and we have seconds here. But we're going to end out with hertz, right? So this is going to be, well, this is going to be 10,000 hertz. Well, hertz and seconds kind of are the same thing, right? They're not exactly the same, but a second is a second and a hertz is per second. And so they're really they're interchangeable, let's put it that way. So that's why we solve for seconds and to get hertz up here. So PRF and hertz. So that was 10,000 hertz, right? Yep. And then number 9, sound wave is created by a transducer, reflects off an object, returns to the transducer. The go return time is 130 microseconds. What's the maximum? So they're giving us the go return time, but they're not. Oh, okay, yeah, they're not giving us the depth. So we have to, this one, it's a 2-step process now. Let's go ahead and we'll put our PRF in hertz is equal to, we know that this is going to be 77,000. That's kind of a constant there, centimeters per second, but we don't know what our depth is. Well, we know we know the go return time, all right? So if we So 130 microseconds, there's a 13 in 130, it's like 113, 0, 13 zeros, or 13 times 10, we know, so we know it's gonna be 10 centimeters. But if you don't know it's gonna be 10 centimeters, we can plug it in. We could plug it in and find out what the go return time will be. So let's see, that would be 1.54 millimeters per microsecond. Now we're just going to add a 0 here, 130 microseconds here. Let's do this down here. So we don't know the depth. Depth in millimeters is equal to 1.54 millimeters per microsecond times, this time instead of 13, because we're not finding the 13 microsecond rule, we're finding this microsecond number, and we divide this by 2, right? Yeah, and so that's going to end out to be, let's see, that's going to 1.5, so that's 200 point something divided by 2 is equal to, I'm sorry, 100. 200 divided by 2 is equal to 100 millimeters, but we prefer speaking in terms of, whoops, that's not what I wanted to hit, I wanted that. We prefer to speak in terms of centimeters, so a quick, just drop it down to centimeters is 10 centimeters. Aha, so now we can say 77,000 divided by 10 centimeters, and that is going to equal 7.7 kilohertz, right? A, A was 7,700 hertz. Okay. Whew, it does get a little confusing. Okay, so that's all the problems. Let's see. There's something I wanted to. Seven's a short. Boy, it's not easy. I think the range equation is easy enough. The 13 microsecond rule. Always remember that PRP and PRF are reciprocals. All you have to do is put 1 over a value to find the other value. I did an example of, well, let me write out the example one more time. I don't want to use other numbers because I'll probably screw up. So let's see. So we have PRP. If we know our PRP and we put 1 over PRP, we get PRF. And the opposite is true as well. All right, so that's one thing. Let's see, for 5 centimeters, what's the pulse repetition period for 5 seconds? So PRP in microseconds is equal to imaging depth. I'm going to say the depth is 5 centimeters, and we're going to multiply that by the 13 microsecond per centimeter rule. That comes 5 times 13 is equal to 65 microseconds. Okay, so 1/65 microseconds. And if we pull out our calculators, well, we could also, let me just write this as 1/0.1234566. 6 zeros in a million, 6 decimal points in a millionths. So that's in seconds. And then if we do the actual calculation, it comes out to 15,385 hertz. So yeah, 15,000 plus pulses in a second. Now, if we go back up to this equation, PRF 77,000 centimeters per second over depth in centimeters, we can do a kind of look at this the other way. So PRF in hertz. Hertz in is equal 77,000 centimeters per second. Oh, itchy nose. Divided by our depth. So do we know our depth? Yeah, why am I? Oh yeah, we do know our depth. Duh. All right, so I forgot where I started from. We do know our depth. 5 centimeters. Those cancel. 77,000 divided by 5 is actually equal to, what was that? Something really close, 15,400. So for all intents and purposes, the same. There are some approximations here, so things don't always work out perfect. And since we're talking about seconds, that is in hertz. So what did we just do? We could find, if we could find our, let's do this in order here. We could find our pulse repetition period by using the 13 microsecond rule times the depth will give us our pulse repetition period. That result, you can put a 1 over that result and get your PRF. Or, alternatively, you could start looking for your PRF by putting 77,000 centimeters per second over the depth in centimeters to find the PRF, the frequency. And you can see, using the same depth, we came very close to the same number. The 13 microsecond is an approximation. It's not truly 13 microseconds. It's very close to that. It's not truly 13 microseconds per centimeter. So that's why we have slightly different answers here. And that's why the 13 microsecond rule is a rule and not an exact science. Okay, yeah, that's all I wanted to talk about for number 7. I didn't open up the test and do what I did last time. which was go through each question and kind of give you a hint question by question. But I do feel like this is a pretty good review. And I'd rather you guys get blindsided by a question and figure it out than not. So, all right, let's end it here. Hasta mañana. Well, no, Monday.